Okay, I'd like to welcome everyone to our Halloween edition of the IMAG MSM Working Group on Multiscale Modeling and Viral Pandemics in GLIMPRINT. Today we have a talk on materials informatics for structure property relationships for liquid solutions. A little bit different topic, and I hope it'll give us some ideas for cross-fertilization. As always, I need to remind people that this meeting is live streamed and recorded and made available in edited form afterwards. This and last week are straddling the 4th anniversary of the working group. Our first seminar actually was November 5th of 2020 on molecular dynamics simulations. And our first meeting of any kind was on October 22nd. So we're right in the middle between the first two meetings of the working group. It's 4 years. So I guess I don't know whether some years we've had an official happy birthday for the group where we've got a review, but this year we're proceeding as usual. The seminars page on the IMAG wiki is back up. Thanks to Jim Sluka for doing a lot of work to try to get that information recovered. Please do take advantage of that archive of materials. If you notice anything wrong with it, please email Jim Sluka, jsluka@iu.edu to get it fixed. As always, Tom, myself, Jim, and Lorenzo are available to take your comments and suggestions. We'd always like to make things more interesting and more useful to everyone in the community. We have a Slack channel, doesn't get a lot of use. We have a Twitter handle, MSM Viral, which you can tag things with. We have the wiki page now that it's working again. We have IMAG LinkedIn page, which you can use, and we have the YouTube channel and the GLIMPRINT web page as well. And so please do help us distribute information on these sites. If you have a publication that you'd like to share on the GLIMPRINT site and the IMAG site, please send them to us. We're always glad to promote material by our group members and make sure that we're serving the community. On the GLIMPRINT site, we can also post job announcements, conference announcements as well, so that if you are interested in having anything that you are doing promoted, please send that to jsluka@idu.edu, and he'll be glad to put it up on the website. Reinhard Labenbacher is currently hiring. People might want to take advantage of that. And Tom Helikar in Nebraska has his big digital twin innovation hub, and he's trying to hire a number of people to build digital twin infrastructure. Tom, do you want to say anything about that search?
Sure. Yeah. Thank you, James. We're looking for multi-scale modelers. We have several positions open for that. We're also looking for a lead scientist, modeling scientist that would work with different subgroups in our research program. And this may be less relevant to this group here usually, but we're also looking for user experience experts and graphic designers.
Great. That's a big project, so it's a great opportunity. And reach out to Tom if you are interested in that or you know people who might be. There is also the ongoing project of Jason Shoemaker at Pitt, trying to recruit people, particularly PhD students, to work on understanding infection and immune response in influenza infection. So that's an open call. I should point out that there are a couple of interesting new grant opportunities. The ARPA-H Catalyst program for computational toxicology and drug development and design. They have a teaming page. You can post your ideas there. I strongly encourage you, if you search ARPA-H and Catalyst, it'll take you to the page where you could fill out your shingle for collaborative opportunities. They had this week in Cincinnati an in-person meeting, doing teaming, but the teaming is open to people who were not able to participate as well. There are a bunch of new opportunities, and SF just announced a first tranche of 7 digital twin awards in the area of biomedical digital twins. So that might be of interest to people. Perhaps we should approach the people who received funding and see about having them speak for this meeting. Might not be a bad idea. There is the call for open source ecosystems, the POSE grant, due January 14th. That's an interesting program because it sponsors community development. People might be interested in that. There is the NOSI, which had October 5th deadline, but the standard NIH due dates on systems modeling of infection and immunity across biological scales, which is of interest to many. Next year, there's going to be a workshop on virus dynamics in Bordeaux, which might be of interest to people here. You could find it here, Virus Dynamics 25, if you do the search, and it's worth taking a look at. Upcoming seminars, November 14th, we have a talk from EMBL Heidelberg. November 28th will be a holiday because it's Thanksgiving. December 12th, we have a speaker from GlaxoSmithKline, and then we won't meet over the Christmas weeks. And then starting again on January 9th, we will have a speaker from the University of Milan. And then coming up later, Adam Knapp from Florida, Chase from the University of Vermont. And we have openings on January 23rd and February 20th. If anyone would like to suggest speakers, as always, we say the same thing. Suggest your graduate students, suggest your postdocs, suggest the people you would like to hear from who've written interesting papers. If you've spoken before and you'd like to come back and speak again, that's okay. People usually have plenty of things to talk about, and so do feel free to suggest ideas for speakers. Please help us keep the roster full. We will have a steering committee meeting tomorrow at 11 a.m. If you think you should be invited and you haven't been, let me know, or Tom or Lorenzo, and we'll make sure you're invited. The topics are going to be the workshop proposal to the Army Research Office and the relationship between GLIMPRINT and the growing Research Data Alliance led by Anna Niarakis for immune digital twins. And so I hope people will join us to discuss those things tomorrow morning in the steering committee. Are there any other announcements before we get to our talk for today? Okay, so I will turn the floor over to our speaker for today. We are going to be hearing again about materials informatics for structure property relationship calculations for liquid solutions. This is going to be, I hope, an interesting talk and a set of ideas that we can perhaps apply in our community. And I will turn the screen share over to you.
First of all, thank you very much for the introduction, and thank you very much for the opportunity to present our work on this platform. It's truly an honor and pleasure to talk about the work that we are doing. So today I'm going to talk about, as James mentioned, a computational framework developed by our lab called Materials Informatics for Structure Property Relationships, abbreviated as MISPR, inspired by the CRISPR project. And I will show you how we are using MISPR for studying liquid solutions. And my background is in chemical engineering, so most of my work is focused on engineering and material science applications. However, most of the properties that we compute and analyze have significant implications to biological systems. So, for example, by understanding materials properties, we can develop innovative solutions to enhance biomaterials, improve drug delivery systems, and advance tissue engineering. So through this talk, I hope to bridge the gap between engineering and biomaterials, and also looking forward to learn more from you on how we can use MISPR to study biomaterials better. Okay, so Just going a brief overview about the data-driven discovery of materials. And as most of us know, over the past few decades, there has been a paradigm shift on discovering and designing new materials using a data-driven approach. And by definition, any data-driven discovery starts with data. So a major component here is integration of big data using high-throughput experiments and high-throughput automated computational engines, which allow us to explore a large chemical and parameter space. And while we are exploring a large chemical and parameter space using these automated approaches, we need to simultaneously advance experimental and computational characterization techniques, which helps us in better understanding structure-property relationships. Along with these tools, there's a growing interest in scientific natural language processing to extract existing useful information from literature. Because even if we are capable of doing experiments or simulations in a high throughput manner, they're still expensive and time consuming. So thanks to advancement in models like GPT and BERT, there's a growing interest in extracting both text and image information from existing literature. And along with these tools, the community should also be focusing on developing collaborative platforms and open source databases, which are absolutely crucial to facilitate transfer of tools and data among researchers globally to reduce duplication. So these different pillars need to talk to each other in order to accelerate data-driven discovery of materials. So the work in our lab is focused on developing high-throughput computational engines, developing characterization computational techniques. We are also implementing scientific natural language processing for text mining and developing open source databases and collaborative platforms. So in the material science and engineering community, with the growing interest on developing open source databases and open source software packages for performing high throughput simulations, there are some of the very well-known examples. There are Materials Project, OQMD, and Jarvis from NIST, to name a few. However, most of these infrastructures are focused on solids, crystalline materials, or nanoporous materials for predicting electronic properties. And compared to solids, much as attention has been given to liquids, multi-component solutions, and solid-liquid interfaces. And in the liquid regime, electrolyte genome was an excellent example where they employed high-throughput DFT calculations to screen electrolyte based on their electronic properties. However, the continuously evolving structural and dynamical properties of liquid solutions demand adopting these techniques both at the quantum as well as the classical scale so that we can study properties of single molecules as well as the ensemble properties of liquids and solid-liquid interfaces. To work in that direction, we developed this computational framework, again coined MISPR. MISPR is an open source, high throughput, multi-scale infrastructure for materials design. So in this framework, we start with an initial database of individual molecular components. They can be, let's say, thousands of salts and solvents we want to explore for energy storage application or for drug discovery, let's say. And as a first step, we perform DFT calculations in a high throughput manner to compute a variety of different electronic properties, such as binding energy and redox potential. And we have several automated workflows to do that. We then use these DFT calculations to generate the force field parameters, which allow us running classical MD simulations in a high throughput manner. So MISPR provides a very seamless integration of DFT and MD simulations, which allow us predicting both the electronic properties as well as the ensemble properties in a high throughput manner. And in this feedback loop, we then extract hundreds and thousands of molecular clusters from MD simulations. We categorize them based on their solvation environment and feed them back to DFT calculations for more detailed analysis of electronic properties. So throughout this process, we are building databases of properties computed from DFT and MD simulations, which are then used to train machine learning models. So MISPR has various uses. It can be used for high throughput screening of potential materials based on property evaluation for a specific application. It can also be used for establishing structure property relationships by exploring a large chemical and parameter space. But as I mentioned, that even high throughput simulations are still computationally time consuming and expensive. So currently we are working on integrating large language models with high throughput simulations, where we start with building a natural language processing pipeline for tokenizing, tagging, and parsing literature data, both the text and the image data. And this helps us in building augmented databases of properties from large language models and combined with high throughput simulations, property prediction. We're also working on feature engineering, and most of the time the features are extracted from cheminformatic packages like RDKit. Some of our recent work shows that custom-made descriptors are very important in developing machine learning models and have a strong impact on many of the predicted properties of liquid solutions. So we need to combine the generic features with the custom-made descriptors. And in this pipeline, we then benchmark different machine learning models and fine-tune the parameters, finally followed by model validation to ensure prediction for a larger chemical space. Okay, so some of the current features of MISPR allows computational database building. So all the properties computed from DFT and MD simulations are stored in a MongoDB database, which is a document-oriented NoSQL database. And MongoDB provides very user-friendly queries and a flexible schema compared to rigid relational databases. MISPR is also built on several existing base libraries, such as Custodian for automatic error handling based on rule-based fixes for failed calculations. So let's say if we are running hundreds of calculations in parallel and 20% of the jobs fail, then Custodian will automatically fix the errors and resubmit the job in the workflow to minimize manual interference. We still might have some failed calculations that needs to be fixed manually. We are using the Fireworks package for managing and executing workflows on multiple queuing systems like Slurm and PBS, and also for monitoring the status of calculations. So MISPR comes with template workflows for various property calculations and provides a seamless integration of DFT and MD simulations. For post-processing, we have our own standalone code base called MDProp tool, which allows computing various structural and dynamical properties. And finally, MISPR comes with a version control through GitHub repository, and it's a very well-documented website, and I will show you a demo of the website at the end of this talk. Okay, so overall, MISPR allows running hundreds and thousands of calculations in parallel to minimize manual interference and generating databases of properties computed from DFT and MD simulations. It takes care of all the underlying tasks from input file generation to managing supercomputing resources, parsing the output data, and also for data analytic. Some of the existing DFT-based workflows include calculation for partial charges, nuclear magnetic resonance chemical shift, binding energy, bond dissociation energy, and redox potential. The MD simulation workflows takes care of all the underlying tasks one would otherwise do manually, from generating the force field parameters and generating the input files and running the calculations of bulk liquids and solid liquid interfaces, and also doing all the structural and dynamical property analysis like residence time, radial distribution function, and so on. The hybrid workflows are the ones which starts from DFT calculations. We then perform MD simulations, do cluster analysis, and then go back to DFT simulations. And an example of that is for predicting experimental NMR chemical shifts. We're using explicit-implicit solvation model, and I'll show you the details of that workflow in a minute. So one of the DFT-based workflow is for calculating redox potential, which is an important metric for identifying electrolytes with a wide electrochemical stability window relevant to energy storage devices, and could also be useful for biological applications such as electron transport chain, where the transfer of electron leads to ATP production. So the workflow employs an adaptive tree data structure with nodes, height, and depth can vary on user inputs to support different type of ionization potential and electron affinity calculations. So for redox potential, there are a variety of different models in the literature. For example, one can simply compute the HOMO or LUMO energy level, or can do a more complex thermodynamic cycle with vertical and adiabatic IP and EA. Another variation exists when we are dealing with aqueous solutions, and then we have to compute a whole thermochemical cycle for a proton-coupled electron transfer reaction. So at the bottom down here is an example of the first and second electron potential as a function of pH for a redox active molecule quinone, which plays a significant role in biological systems, particularly in electron transport chain. So overall, the workflow is quite flexible with a tree-like structure, with the only required input is the input structure and the reference charge. And the user can perform 1 electron or n electron calculations in gas phase or in solution phase. Another example of a DFT-based workflow is for calculating the bond dissociation energy, or BDE. BDE is another very important property. It's a thermodynamic metric, which is very widely used to determine the stability of chemical compounds and their chemical reactivity and selectivity. And it's one of the first metric in characterizing the dominant reaction pathways in biofuel combustions, drug metabolism, and also for screening electrolytes for electrosynthesis and energy storage devices. So here the BD calculations generally are very intensive because we need to optimize the reactant and all possible fragments, and then also estimate their Hessian, which makes these calculations very exhausting. So the BD workflow in MISPR allow running these calculations in a high throughput manner, where the only required input is really just the principal structure, and it optimizes the geometry of the reactant and all possible fragments, outputs their enthalpy, and then calculate the bond dissociation energy. The workflow supports both homolytic and heterolytic bond dissociation of neutral and charged species. It also comes with an option to open bonds that are part of a ring, and also have an additional option to do local energy minimization, which is helpful and saves computational cost instead of just directly sending the fragments for geometry optimization. Very useful in cases where we are opening bonds that are part of a ring to prevent them from reclosing. The MD simulation-based workflows are built upon DFT calculations. So most of the systems that we are interested in are multi-component solutions. So we start with the DFT calculations of individual species and generate the force field parameters. Currently, MISPR provides support for generalized amber force field and OPLS force fields, but the user are allowed to provide any force field that they want from literature, let's say. The next step is building the data file where the user can provide information about concentration, temperature, and any other optional parameters. And then we apply the default recipes, or the user can override the recipes of MD for different ensembles. And then we finally analyze the trajectories for a variety of different structural and dynamical properties. And that's done in an automated fashion using MDProp tools, which has routines for various structural and dynamical properties, such as radial distribution function, viscosity, number density at interfaces, and so on. So using this, MISPR is capable of building databases of properties computed from DFT calculations, from MD simulations, and databases of force field parameters that we are using. Each computed property is stored in its own respective collection, but along with the actual property data, we also store a bunch of different metadata, such as the molecule information, software information, post-field references, etc. And this information is very important for transparency in data sharing and reproducibility. So in the next half of this talk, I'll show you how we are using MISPR for elucidating solvation structure in multi-component liquid solutions. And I think solvation structure is really the key to understand liquid solutions and design optimal solutions for a variety of different applications. And it's the intimate dance of the solvent around the solute, which control the overall physical and chemical properties of a liquid solution. And it's often not trivial to extract this information, even for simpler systems like electrolytes, where we have a cation, an anion, and a solvent or a binary solvent mixture. And the reason being, first of all, there's an extremely large chemical and parameter space that needs to be explored to be able to have any predictive capability. Any small changes in the molecular features of these components results in radical changes in the mesoscopic properties. For example, depending on the structure, the molecular features of cations, anions, and solvents, that can lead to formation of either solvent-separated ion pair with vehicular diffusion or contact ion pairs with structural diffusion. So it's of paramount importance to really understand this complex interatomic interactions. So the most widely used methods for characterizing such interactions are nuclear magnetic resonance, or Raman, and infrared spectroscopy. In particular, NMR spectroscopy is one of the most widely used and a very powerful technique to probe the structural and dynamical properties of liquid solutions, because it can provide a lot of details about the solvation structure, including connectivity, stereochemistry, and conformational dynamics. However, the experimental NMR techniques are limited by their temporal scale and low sensitivity, which makes it difficult to deconvolute this experimental spectrum and assign it to specific stable species present in the solution. Also, the time average spectroscopic response, often referred to as a static solvation structure, which leads to oversimplification of structural complexities. So spectroscopic fingerprinting, such as labeling these resonance and vibration frequencies, are often done using either DFT or AIMD simulations. However, these simulations have their own challenges. First of all, in order to really capture the solvation environment, we need to include the explicit solvation structure, which becomes very computationally expensive, and that results in inaccurate account of the solvation effect. The DFT calculations fail to fingerprint the temporal evolution of solvation structure under exogenous and endogenous condition. And most of the time, we end up focusing on one particular solvation structure that matches with the center of the experimental spectrum. And even that structure is generated manually using trial and error-based approaches or using chemical intuitions. To overcome some of these challenges, we developed computational spectroscopic analysis tools in MISPR. And in this framework, we start with the structure of just individual components. It could be SMILE strings or the XYZ or any other preferred format. So in our case, we are working with electrolytes with alkali metal cations. So let's say it's a cation, an anion, and a solvent. We first begin with the ESP workflow that optimizes the geometry of individual species and generate the force field parameters. We then run the MD simulations, where the user can provide the composition and other optional parameters, their own force field if they want, for example. Based on the structural analysis from MD simulations, we extract hundreds and thousands of molecular clusters from MD simulations and categorize them based on their solvation environment. From there, we extract the top clusters, which are then subjected to the NMR workflow. Now, in the NMR workflow, we re-optimize these molecular extracted structure and then calculate their NMR chemical shifts using DFT calculations. And all the data and metadata is stored in a MongoDB database for easy retrieval and analysis, which can then be compared with the experimental spectrum. So I'll show you an example of where we used this framework to resolve discrepancy in the literature about the solvation structure of an electrolyte, which is relevant to magnesium ion batteries with magnesium TFSI salt dissolved in DME solvent. So this electrolyte has been studied extensively in literature for its solvation structure, and there are several discrepancies about its solvation structure. Some of the previously reported SCXRD data suggest that we are forming solvent-separated ion pairs in the solution, so the cation is only surrounded by the solvent molecule, whereas the previously reported computational data suggest formation of contact ion pairs in the solution. And this tiny difference between solvent-separated ion pairs versus contact ion pairs is very important for designing electrolytes for batteries, because this determines what will be migrating toward the surface and what will react and how it affects the battery performance. So to resolve this discrepancy using the NMR workflow, we simulated that electrolyte and we extracted more than 300,000 clusters from MD simulations. We categorized them based on their solvation environment and based on their probability of occurrence in the solution. So this top structure here is the one that has a probability of occurrence of more than 80%. And the predicted NMR chemical shift, this red bar here, matches exactly with the center of the experimental spectrum. Okay? And it's the same structure which was previously reported by the SCXRD experiments, which suggest formation of solvent-separated ion pairs. However, the key point here is that liquids cannot be expected to have a single static solvation structure and can rather have a spectrum of multiple stable and metastable species. And these structures are hard to extract using either experiments or based on chemical intuition. So a key advantage of this workflow is that it not only detects the most stable structure, but it also identifies other stable structure present in the solution. For example, here, this broad line width of the experimental spectrum suggests that we actually do have multiple stable species present in the solution, but we cannot identify them using experiments. So using the framework, we identified 5 other stable structures which are present in the solution and likely control the properties of this electrolyte. So we were able to accurately predict the NMR chemical shifts, but the NMR chemical shifts are very sensitive, of course, to the solvation environment, and also a lot of different things that we do in simulations. For example, the force field parameters that we use and the DFT level of theory that we use. So we identified different factors which affect the accuracy of these NMR chemical shift prediction. I would highlight some of them. So a key factor about the accuracy of MD simulations is, of course, the force field parameters that we are using. So here we tested the 3 commonly used force field for this electrolyte, which includes generalized amber force field, GAF, OPLS, and polarizable OPLS force field. So on the left-hand side, we are looking at the radial distribution function of the cation with solvent and the cation with anion. And you can see that different force fields give very different results. If we use GAF, it suggests that we have a very weak cation-solvent interaction and a very strong cation-anion interaction. If we use polarizable OPLS force field, it suggests very strong cation-solvent interaction and almost negligible cation-anion interaction. This is also reflected in the coordination number analysis. If we use GAF, it suggests formation of aggregates. If we use OPLS, it suggests formation of contact ion pairs. If we use OPLS polarizable force field, it suggests formation of, solvent-separated ion pairs. And that could be one of the reasons why experimentalists don't trust computational people, because right now, depending on any force field, I can predict any type of solvation structure. So we further dig deep into the different type of configurations that we can get out from these different force reals. We extracted the top 6 configurations. And overall, we found that GAF and OPLS results in over-prediction of cation-anion interaction. Whereas for this particular electrolyte, polarizable OPLS force reel gives more accurate predictions with more homogeneous structures where the cation primarily interacts with the solvent. So based on the NMR experimental results in this work and the previously reported SCXRD data, we concluded that for this electrolyte, polarizable OPLS force reel gives the most accurate solvation structure. Another key factor for accuracy in our calculation is the level of theory we use in DFT calculations. So here we did extensive benchmarking of different functionals and basis sets. I'm showing you results for the prediction of 25 magnesium NMR chemical shifts, for which we tested different functionals from B3lib, MO62X to omega B97X, and different basis sets from 631 plus G star to TEF2TZPP. So again, you can see here, especially for the lower basis sets going from top to bottom, we get very different predictions depending on what functional we are using. Going from left to right, the predictions improve with increase in the basis sets. So in this work, we considered 3 criteria to select the most optimal level of theory. It should be accurate, it should be computationally cheap, and it should have lesser tendency to fail because we're trying to run these calculations in a high throughput manner. So based on that criteria, we identified 2 levels of theory, which gives the most accurate prediction of NMR chemical shifts. We did similar benchmarking for carbon and proton NMR chemical shifts, and the details are in the supplementary information of this paper here. So the key take home away here message here is that benchmarking is absolutely crucial, which often takes a back seat and it's considered given, but it's also very time consuming and demanding but it's important to boost confidence in our predictions. We were able to generalize this MISPR tool on a variety of different electrolytes so far and establishing the concept of multiplicity of solvation structure in different electrolytes used in sodium, lithium, and magnesium-ion batteries. So we have tested it for different type of electrolytes. A further application of this framework is for studying challenging molecules like biologically active natural products or pharmaceutically relevant molecules with complex stereochemistry and flexible conformation. And in those cases, elucidating solvation structure is of paramount importance to understand its biological activity. So here we use the framework to accurately identify and distinguish the 4 stereoisomers of pen and beta-lactam in chloroform, which is an antibiotic related to penicillin. So that hopefully shows the generalizability of the framework, that it can be used for a variety of different type of systems in diverse applications. Also, the framework significantly cuts down the time and efforts required to do this calculation. Here is an example where we performed 300 carbon and 600 proton NMR chemical shifts in less than 24 hours for 100 molecules downloaded from STBS database. And the framework performed the entire geometry optimization calculation and calculate the NMR chemical shifts using very high level of theory. And you can see here that we got remarkable agreement in the predicted chemical shifts and the experimental value, which shows that the frameworks is extremely helpful in generating large-scale databases of both traditional and non-traditional nuclei and significantly cuts down the time required to generate the input file, do the calculations, and doing the analysis. We store all the data and metadata in our documents in our computational databases. So here is an example of the NMR document where we store the molecule information, the metadata like SMILES and INCI string required as input for machine learning models, the calculation results, which in this case, the NMR tensors. We store the DFT level of theory, the software version, time required to do these calculations. And again, these information are very important for people to be able to reproduce our results and transparency in data sharing. Lastly, I would like to emphasize again that MISPR is an open source code base free for anyone to use. We tried to make a very well documented website so that it will help users to get started with MISPR. So here's a demo of the website where you can get an overview, some of the things that I talked about today. At the back end, MISPR is using Gaussian for DFT calculations and LAMPS for MD simulations. The installation is pretty straightforward using pip install. If you have used Python, familiar with Python, you'll find it very easy to do. It provides all the information of how a user can build their own databases, run and test workflows, and query results from database. Although like I mentioned, we are using fireworks, and more details about building workflows can be found here, but we tried to give a brief overview of what it means to build a workflow in MISPR, and also user can make their own custom workflows depending on their requirements. So currently we support DFT-based workflows, MD-based workflows, and hybrid workflows, which starts from DFT, perform MD simulation, and go back to DFT calculations. In the helpful links, we have our Code Ocean capsules, which we use to train high school students and help them in running quantum chemistry and MD simulations in a high throughput manner using these Code Ocean capsules. So that's another useful resource to learn about MISPR and get started with it. But again, if you have any questions, please feel free to reach out to us and we'd be happy to help you in getting started. So hopefully I was able to give you some idea that MISPR allows exploring a large chemical and parameter space over a wide spatial and temporal scale to study materials properties by seamlessly integrating DFT and MD simulations. When we talk about liquid solution, a static solvation structure is merely a snapshot of the complex dynamic processing. And in liquids, we have actually a spectrum of multiple stable species, which are hard to identify using experiments alone. So MISPR helps here in accurately and efficiently identifying multiple stable species in complex solutions by analyzing the experimental NMR spectrum. And with this, I would like to thank the people who worked on this project. Most of the work that I presented today was done by my graduate student, Rasha Athwi and Matthew Bliss. I'm thankful to the funding from LG Energy Solution for this work and computational resources from Stony Brook University Institute for Advanced Computational Science. We try to do extensive benchmarking and validate our results as much as possible. And for that, I'm extremely thankful to the experimental collaboration from PNNL, NYU, and Purdue University. And with that, I'll stop. Thank you so much for your attention, and I would be happy to answer any questions.
Thank you so much for your talk. It was very interesting, but because it's so far away from what I'm used to deal with, I'm more into the worlds of cells and those kind of things, a little bit higher scale there. But one thing that came to my mind is if trying to collide these two worlds, right, these two scales, if there is any possibility of, or you see this tool being able to predict interaction with cell membranes, for example, for us to analyze some possible toxicological response to chemicals, for example.
Okay, yeah, that's a very interesting question. Yeah, like I said, we are primarily dealing with small organic molecules, but I don't know, are you using GROMACS or LAMPS to do any of your simulations?
No, I use CC3D. I'm doing actually a tissue level of simulation, but there is interest from companies, for example, to understand how chemicals affect cells.
Okay, so we currently with MISPR, we are limited to these two scales that we are dealing with, the DFT calculations and MD simulations. And there are a lot of people who are using packages like Chromax and LAMS for doing simulations for biological systems, and all those can be handled by MISPR. But at least right now, I cannot claim that it can handle larger scales because we don't have that capability right now.
I wanted to come back to the workflow, maybe your slide 11,
Okay.
and maybe you could tell us a little bit more, because while the particular calculations that we do are quite different, some of the issues that you're addressing are quite similar. And I think it was your slide 11 and slide 24 where you were talking about how you maybe we can. So you have this database, and you have this heterogeneous database.
Yeah.
Can you talk a little bit more about how this is organized and how you work with it? I know you showed us a schema for it on slide 24, but why don't we start here and tell us a little bit more about how these databases are conceptualized and organized? Maybe start with the schema here. The first question I have is, some of these kinds of representations are standards that I recognize. How much of this did you have to invent in terms of the schema, and how much of this is standard in the molecular dynamics or NMR worlds?
So we kind of had to, yes, invent our own schema, because as far as I know, so the existing databases, for example, for NMR chemical shifts, only include chemical shift of single molecules. They don't have chemical shifts of clusters or liquid solutions. So they do not consider the solute-solvent interactions. So we had to come up with our own schema. With that being said, MongoDB has been used widely in the material science community. So we definitely learned and leveraged a lot from there of how and what is the useful information to store. So that it's stored more like a Python dictionary, if you're familiar with that, with the key and the values. So what information to store, that totally depends on us, but we looked at some similar other MongoDB databases in the material science community and tried to adapt from there to ensure that we are saving all the useful information. Does that make sense?
Well, so that's very helpful. So when you have calculation results, so you potentially different calculations will give you different types of result. And so I'm trying to understand. Maybe you could walk us through this example a little bit more, in a little bit more detail here.
Yeah. So let's say if we are doing, so some things are of course common, like for every molecule we are saving information about. We are using the module, which is here PyMedGen core structure. This is the ID number of that particular calculation and that particular molecule. It has a charge of 0, spin multiplicity of 1. We can store many other keyword arguments, but that's the bare minimal. Here is the SMILE string of the molecule, the INCAI strings, which are used for machine learning models, the chemical formula, the energy extracted from our DFT calculations. So following from this line onwards, we wrote a Python code and tells it what information we want to extract from our output file, be it from DFT calculations or a LAMS output file. And then from this line onwards, we have different information stored in different documents. This is an example of a DFT output file document. So we are storing the output energy. This information is given in the output file from our DFT calculations, the tensors for the NMR. This information is in the output file, but also in the input file of our DFT calculations of what functionals and basis sets we are using, what type of solvation model we are using, and what solvent we are using. So we are using PCM solvation model here, and we are using chloroform for that. And it stores how much time it requires to do this calculation. the version of Gaussian software that we are using, and of course the date and time to run that calculation. So all this is done using a Python script, which I think, we learned from similar examples in the material science community from Materials Project, who was also using MongoDB database and doing similar things.
So, I mean, at the beginning, you talked about trying to have basically interconnectability between packages.
Mhm.
And so I guess what I'm trying to understand, one of the things that we face in our community is that we don't actually have very good ways of sharing model specification. That's probably going to be a bit different here because the kinds of things we have to specify in our model are somewhat different. Although what are called center models actually are very much like molecular dynamics models. The computationally they're very similar. The other thing that we have to do a lot is that we run lots of, as you do, we run lots of replicates of simulations with large numbers of parameter sets. And we have to be able to archive those and access them in a consistent way. And that's something that is an area of interest to us.
Okay.
You have something which we don't have, which is that you have standard ways of specifying your molecular species.
Okay.
And that's something that we lack. There isn't an agreed upon way of specifying multicellular, well, cellular behaviors and their properties, and that's a problem that we face.
Okay.
Now I was wondering. So this looks like, I mean, clearly as a Python dictionary in a sense, it's a very simple thing to work with.
Yeah.
Do you have at the moment are there any other packages that can read these result databases and work with them? Or are you exchanging this kind of information with people who develop other software tools? Or is this the first
Yes.
tool that uses
So
particular structure?
yeah, we are. So basically, we built MISPR on 3 existing packages in the materials community. We are using PyMidgen, as you can see here. So we forked the repository and modified the code for our own use. And we are using Custodian for error handling and Fireworks for workflow management. So we recently merged our changes for the Custodian package back into the master repository. So we are contributing to other codes as well. And I think one of the points that you raise is about heterogeneity of data, which we faced a lot of problem with that as well initially, because we were integrating data from different scales of simulations. So that required extensive programming in Python and building scripts that allow us to do that. But yes, there are other packages which are able to read this information as well.
So you do see this as then a framework for data interchange and model interchange with other methods.
Mhm. Yeah.
Jim, looking at the metadata annotations here, how much could we think about this? How different would it have to be to think about this kind of structure in our world potentially?
The challenge is just figuring out what are those red tags that we'd have to include. You can certainly imagine doing it, generating a record for a particular cell type, including, normal volume, surface, links to the cell ontology and tissue ontology and things like that. But boy, it would take a fair amount of work because of how heterogeneous the modeling domain is in biology.
Yeah, I guess you raise a good point, Jim. If I had to imagine, something would be all the characteristic that all cells can show, and then you flag that as a yes or no, which is a huge job to do.
I was curious, are there any existing MongoDB databases for the type of systems that you're interested in?
I don't think anybody has tried MongoDB. I was actually making a note that we should be looking at this more seriously. the software that our group develops, and many other packages as well in our community, are Python scripted in Python, and they may have a back end that's written in C++ or in CUDA, but the front ends are almost always Python. And so, and our software actually uses, for internal representation, uses Python dictionaries as its fundamental architecture. So actually, this kind of Python dictionary architecture for flexible specification is quite attractive. It certainly looks more flexible than a JSON file, for example. And so that is quite interesting to us.
And it also comes with a very nice GUIs, which is, I think, MongoDB Campus, and there are other very nice GUIs, which makes it very easy to query the data. So you can query it based on any of the keys which are shown here. So we find it very useful instead of dealing with files manually.
Great. Well, that's something that we will definitely look into. Are there any other? We're getting towards the end of our hour. Is there any other questions from Jim? Do you have anything you want to add, Ellen?
No, sorry. It was a great talk though, and I learned a lot.
Okay.
Thank you so much.
Sorry. Okay. I want to thank you again. I didn't mean to interrupt you there. Thank you again for coming. And we will be eager to look at the software and try to understand better how we can learn. The molecular dynamics community is very advanced in terms of software tools and standardization compared to ours.
Yeah.
So whenever we hear talks in this field, we appreciate how much we have to do to reach the standard that you take for granted. And seeing people develop these kinds of extensions is very exciting to us.
Well, thank you so much for the opportunity. But I think the type of systems that you are dealing with are way more complex, and I see the application of MISPR very easily transferable to small biomolecules, but cell membranes and other large-scale simulations, I think they are still, far from our reach so far. But thank you so much for the opportunity. Like I said, this was a very different platform for me, and I learned a lot. So thank you for the opportunity to share our work here.
Okay, well, I thank you again, and I'll see our audience in 2 weeks.